Welcome to the session of the whole atmospheric working group. On behalf of the whole atmospheric working group team, I'm going to start this session by giving a short overview, which I hope will show up very soon on the screen. Just FYI for any presenters in the room, this laptop that is here in the front does not control anything, okay? This is just so you don't have to stand like this, okay? So just so you further ado, let's jump in the overview and developments that we've been working on in the past months. Just as a reminder, the models that are relevant to our working group comprise the WAWG with model top ranging from 10 to the minus 7, 10 to the minus 9 hectopascal. We have vacuum with a top at about 10 to the minus 5th hectopascal, corresponding to 140 kilometers. And we also have the CAM-MT, which is short for mid-top, and it has a model top at about 80 kilometers. So our priorities for the development are still that we have a good QBO in both model resolutions at 1 and 2 degrees. We want to have a good seasonal cycle in wind and temperature in the stratosphere and mesosphere. So we also have realistic impacts on the chemistry. And we also want to have a good thermosphere extension of the SE dicore and the ionosphere thermosphere climatology. And I did it, I just clicked on the laptop. So what we are working on right now is no surprise, our classic. We are working on the QBO tuning. So it's starting to look reasonable. It's still not perfect. I will show you results on that in a few slides. We have done base runs which have shown that the stratosphere and the mesosphere, also the lower thermosphere dynamics and seasonal cycles are okay, like there is room for improvement, but also we have not found any major issues. We have updated the nitrogen chemistry in the lower thermosphere, which improved the thermosphere temperature and the neutral density in WAWG. Also, we have updated the Shapiro filter in WAWG for the SE dicore. Additionally, we are working on different gravity wave parameterizations. The one that is mentioned here is used for the tuning of the high-resolution WAWG. And last but not least, also exciting, ADF is now supporting vacuum output, so we can have vacuum-focused results from the ADF. Some known issues and biases that we found in our base runs are that we are still too dry with a tropical stratospheric water vapor tape recorder, especially in the 2-degree runs. And also we are still working on the robust calculation of the TEM diagnostics. And so here are now a few results from the base runs. So on the top is the 2-degree run, on the bottom is the 1-degree run, and these are already results with the ADF package I want to mention. And you can see that the amplitude looks reasonable, but the QBO, if you look at the Hofmeller diagrams, you notice that the westerly phase is too strong and the easterly phase is not long enough. So this is something that we need to address, and we hope to address it with a new gravity wave parameterization. Then here, these runs now include the newly developed moving mountain parameterization, and also, as it did with CAM, it also had a really positive impact on the polar vortex in vacuum. On the left-hand side 2 degree, right-hand side 1 degree. The top panel shows vacuum, the middle panel era 5, and the bottom shows the differences. And you can see that especially including this parameterization led to a real improvement in the representation of the polar vortex jet axis, which is especially important also in the southern hemisphere. And here, just real quick, are the seasonal cycles. The polar vortex in the northern hemisphere is still too low, so we have to tune this up. But overall, it agrees quite well, and especially here in the southern hemisphere, the differences are on the order of like 5 meters per second between Era 5 and WAWG. So our current development plans are at the moment that for WAWG that we want to develop a new method to calculate the zonal means. For TEM fluxes, I will talk about that more in a minute. We are also working on inline photolysis with the TUVX model, and also vacuum with the MPAS as a dicore is in development. For vacuum mix, we are working on a two-way coupling with Gamera, and then also we are working on an improved ionosphere, dynamo and transport, scale-aware gravity wave parameterization, and also on the interface with JEDI for space weather data assimilation. Also, we are thinking about already long-term, so we want to further reduce the model costs. We are aware that especially for universities, vacuum and vacuum mix are expensive to run. So we are looking into different ML applications, and one potential venue could include that we replace the troposphere from a physics-based model to an ML model, and also include different machine-learned parameterizations, like, for example, aerosol and microphysics or gravity waves. So I promised to talk more about the zonal mean flux calculations for TEM. This is work mostly done by Francis Witt, and also Justin Richling has worked a lot on getting these fluxes into ADF. Basically, how the issue is in this project is that in SE, the dicore, with the SE dicore, the grid is unstructured. So you basically cannot calculate a zonal mean for the TEM fluxes. So what Francis did is that he included an ESMF library where he could, on the fly, regrid this unstructured SE grid to a lat-lon FV grid, which would then make it rather straightforward to calculate zonal means for the TEM calculations. And this was very successful. Like it only added 1 to 2% cost, and like it was a tremendous effort from Francis. However, like working on it, we noticed that there is a potential noise issue, especially on the high latitudes, which we still need to figure out. So Michong, Francis, and Justin are working on this. Then June has implemented an inline photolysis was based on a lookup table approach, and the issue with this approach is that the lookup table approach didn't include the real-time simulated aerosol or cloud content. And so with this new approach, we are actually taking into account the real-time aerosol content, and based on that, the actinic flux can be calculated. And in a first test with the Pinatubo eruption, June could show that the sulfate aerosol layer in the stratosphere can have an effect on the photolysis rates in the atmosphere. Then vacuum is also extended to the MPAS dicore. This is work that Sude is working on, and she already has a first paper on it where she had a stable run with the MPAS dicore and a 70 vertical layer vacuum version with a horizontal grid spacing of 120 kilometers. And this is published and in this paper here. And currently, she is working on extending this development to a full chemistry model with the new 135 vertical level grid. And also they are working on the constant pressure upper boundary development, and which requires more testing, and this is especially developed for the geospace applications. And additionally, they also are working on regional refinement down to 3 kilometers, which over CONUS, which is especially important for the CIMA S2S project. And then, last but not least, very exciting work is that vacuum X is now coupled with Gamera. The background for this is that the forcing from the magnetosphere in the high latitudes is one of the largest uncertainties for the upper atmosphere response to geomagnetic storms, and mostly empirical models fail to reliably capture this high latitude forcing. And so NASA, Center for Geospace Storms, and HAO have joined forces and have recently completed a two-way coupling between vacuum X and Gamera, which is a first step to a whole geospace model. So in summary, we are working on evaluating the stratosphere, mesosphere, and lower thermosphere dynamics within the CESM3 context. We are also working on the inline photolysis. Vacuum will have in the future an MPAS dicore and is also heading towards a whole geospace model. The development tasks that we are facing are that we need to improve the TEM calculation. We also need to implement low-frequency tropical gravity wave parameterizations that might help with the biases in the QBO that I pointed out earlier. We also want to include another vertical grid that is based on CAM to synthesize more with CAM and also make the 2-degree model even cheaper to run. And we also need to, we are still working on the inline photolysis calculations. At the moment they include aerosols, but June is working on also including the cloud effect now. And of course, we are exploring ML options for tuning and replacing the troposphere. So thanks for your attention. Are there any questions? Do we have time for questions? I don't know, Daniele. I'm asking you. Yeah, let's do. Okay. Good. Then the next speaker, Mijong.
Okay. I've been asked by both Martina and Mijong to introduce people. Okay, so first talk for today, we have dynamical and chemical variabilities in CSM3 WACM 7 by Mijong.
Thank you, Daniele. I forced you to introduce me.
No, it was a great pleasure.
Okay, awesome. Oh, great. Okay, hello everyone. I'm Mijong, and first of all, I'd like to thank my co-authors, everyone on the list. In fact, I'd like to thank many of you in the audience. And you might notice my title is very vague or generous. So you have no idea what I'm going to talk about. What I'm going to talk about today is, sorry. I was looking at my screen here, it's not moving. Sorry. Okay, so what I'm going to talk about today in this talk is I'm going to compare WACM 7 with WACM 6 and some of the measurement observations. So I'm going to talk about three things. Number one is stratospheric QBO. Number two is tropical water vapor tape recorder. And number three is southern hemispheric polar cap, temperature, and total column ozone. So QBO in WACM 7, it was very different from the QBO we've known in the past. So we've looked at it, what is the reason for this different QBO in WACM 7, and we fixed one thing. It turns out the effect of HB diffusion, which was included in the model, was making the QBO amplitude too weak. So we decided to remove the background and stable mixing, then we were able to improve the QBO amplitude. So the figure you're looking at the bottom is, so x-axis is time, about 20 years, y-axis is pressure, zonal mean, zonal wind. This is what the QBO in WACM 7 looked like based on one of the recent tags. So it's still not perfect. The amplitude is pretty good, but it's too fast. And so we have more work to do. So one thing I would mention here is that we are using 2-degree WACM. The hope is to transfer our knowledge we learn from 2-degree simulation to 1 degree. But to be able to do that, you have to understand they might not be the same, because 1 degree, you can imagine they can resolve more waves than 2 degree. So this is one of the figure that I already have in the past. Let's compare QBO in 1 degree versus 2 degree. So these are the composite of, for example, westerly phase of about 20 years. So on the left is 1 degree simulation. This is actually WACM 5.4, the same version Rolando and Yaga used in their paper in 2019. And on the right is WACM 6 degree. So they do have pretty reasonable amplitude and period, but if you look at the detail, this is consistent with Martina's talk, in fact. In 2 degree, westerly is maybe stronger, easterly is weaker. Why is that? We can look at then what's contributing to this different QBL. So we can look at 1 degree and 2 degree, and also we can separate the contribution from resolved wave, which is EP flux divergence, which you're looking at the top panel, and the bottom is gravity wave drag based on parameterized gravity wave. And overall, they look similar. This is a composite of downwelling westerly phase. So they do capture similar features. But if you focus on the figure on the right low bottom, the red is much larger than the left figure. What that means is larger contribution from parameterized gravity wave play bigger role in 2 degree. So this one has some consequences. So 2 degree and 1 degree might react differently to the same parameterization. And if there's stronger convection, they might react differently. So I want you to remember this difference in 2 degree and 1 degree. Now let's look at water vapor tape recorder. So the figure you're looking at on the left, x-axis is time from 1984 through almost present day. Y-axis is pressure. So what you're looking at is water vapor mixing ratio based on satellite observations for this long period. And here, once again, I want you to remember 3 things. 3 is my favorite number. So number 1, as you can see, there is large year-to-year variability in water vapor tape recorder. They're not the same every year. And you can separate, there is wet phase, there is dry phase of tape recorder. So wet phase is influenced by something called Northern Hemisphere summer monsoons. As you can see from the figure on the right upper panel, this water vapor mixing ratio is enhanced over both monsoon area. And for dry phase, this is actually different from wet phase. Tropical cold point temperatures are important. So now, let's look at WACM 7 water vapor tape recorder. So you're looking at 2 figures. The bottom one is water vapor tape recorder from WACM 7 2 degree simulation, and top one is actually from MLS. MLS is satellite measuring water vapor from 2004. So I just picked just random 6 years. They're not the same year, but you get a sense of how they compare. So if you compare the bottom figure to top figure, the more greener at the bottom, which means is that the entire stratosphere is drier in WACM 7, including both wet phase and dry phase. And if you look at the arrow that I pointed on the figure, it looks like wet phase in WACM 7 does not propagate high enough. It stopped at lower altitude. That's interesting. So what I decided to, just for fun, I did two experiments. One is, I'm going to look at dry phase first. My question was, is WACM 7 too cold? Because dry phase is controlled by cold temperature. So once again, I'm comparing temperature and water vapor from MLS at 100 hectopascal in the tropics. And bottom figure is the same format. I'm comparing water vapor from temperature from WACM 7. I picked 100 and near 100 hectopascal from model. So I put circles on the left. So minimum temperature in MLS is around 190. WACM 7 is 192. So my simple answer is that It's not that WACM 7 temperature is too cold, controlling water vapor too low. And for fun, I added this Clausius-Clapeyron equation based on, okay, when you get this pressure, temperature, you have this amount of water vapor. So this number shows if temperature is higher, water vapor can be higher, but that's not the case. And now, let's look at wet phase. So if you remember, wet phase of tape recorder is controlled by or influenced by Northern Hemisphere summer monsoon. So monsoon season is from July to August. But this high water vapor coming in through the monsoon, it can go up through time. So let's look at the bottom panel. So bottom panel is, once again, is an observation. But this time it's called CESM ISS, different satellite. So on the left is September and November, January of just 1 year. As you can see here, the high water vapor coming in the Northern Hemisphere, it goes up altitude. You can track this high amount of water vapor going up with time. Now, the top panels are from WACM 7 2-degree simulation. You can actually see high water vapor coming in the Northern Hemisphere, but they don't really last long. By January, it just disappeared. And we also did this simulation, just same configuration, WACM 7 2-degree, and we changed topography to a little bit rougher topography. And I wanted to look at the water vapor, if it does have any impact, and it looked like, especially if you can look at the figure on the right bottom panel, so dry phases of water vapor tape recorder is drier. Oh, what happened? Okay, so that's one thing I've learned by comparing these two simulations. And now let's move on to southern hemisphere polar cap temperature, and I'm going to look at some ozone later. So top figure is 20-year climatology of southern polar cap temperature. Okay, I'm really confused. My screen keeps moving and not moving, sorry about that. And bottom figure is WACM 7 run that I've been comparing. So if you look at the July temperature, the minimum temperature is pretty similar, about 190 K. But there are differences, especially temperature is maybe warmer high up and colder at the bottom. Let's look at the difference. So once again, top figure is WACM 6. This is from a paper by Andrew et al., Gettleman et al. 2019. And bottom figure is WACM 7, the difference between WACM and MERA 2. So in WACM 7, we did have this warm anomaly or bias in winter going into spring. This is related to delayed breakdown of polar vortex. In WACM 7, as you can see, this warm bias is more significant. And I don't know. But this, I don't know why, we have to work on it. But the consequences or what's related to this temperature bias in the model can be total ozone column ozone. Because when the temperature gets low, it's a threshold of 78 degrees Celsius, which is 190 K, and more active heterogeneous chemistry can destroy ozone. So you can relate, if it's too cold, we have too little ozone. So this figure is from, there are multiple lines here, so June created this figure. So black dots, look at the black dots. These are based on observations. And blue dashed line is what we used to have in WACM 6 SD. It was a little bit higher than observations. And if you look at the green line, this is WACM 7 2-degree. We have a little bit even higher ozone. This is related to maybe warmer temperature. And now, the red solid line is 1 degree simulation. Ozone is much lower. You can relate this, maybe temperature is too cold. Is that true? So we can look at the temperature. Now, so June compared this 2 degree and 1 degree run just for September, November in southern hemisphere, comparing two temperatures, and the anomaly figure on the right shows 2 degrees much warmer, 1 degree is colder. And if you look at ozone, you can see this colder temperature transfer into too low ozone. So that's it. And my summary is, if WACM 6 did something well, we want to get there. And if Wacom 6 did not do something well, we want to fix it. That's our goal. Thank you for attention. Question or? Oh, okay, question.
Thanks for the talk. I think the Barrett scheme for convective gravity parameterization has some scale-sensitive parameter like a cloud fraction. Have you considered tuning it for different resolution?
Yes, yes. So we've been doing lots of tuning in the past almost 2 years. And one thing I wanted to mention is, so we're still working on it. So we have something called cam tag. It changes quite often, and different cam tag produce different QBO. So we are learning by tuning the QBO with these parameters, but we get different QBO with each tag. So by maybe finalizing our model, we can find perfect combination of tuning parameters and be able to do good QBO. Thank you.
Very nice talk. So in the polar region, is the moving mountain parameterization operating in both?
I believe so, yes.
Are the tunings different? So you might have to
Martina said
tune
no.
that. And another thing you might have to worry about is that was one realization. So you could have, if you average 3 or 4 realizations, you might on average get what Mara or whatever you're comparing to gets. So it's hard to really say just looking at one run.
Yeah, that's great. That's great.
When you did the tape recorder, that was not a nudged simulation. Did you do a nudged simulation to see if that tape recorder looks better?
Not yet. So Martina so watch your head. We haven't done it yet.
Yeah, then you could see if the temperature actually matters further.
Okay, great. Thank you. Okay, then next speaker.
Time for next speaker. And next we have a remote presentation by Selina Zhang, record higher ozone in southern mid-latitude tropopause region driven by dynamical and chemical effects of the 2019 southern stratospheric warming.
Hi,
Dawn,
yes.
you can share your screen.
I'm not sure. Hi,
Dawn,
yes.
you can share your screen.
I'm not sure if I
Or
can
is the,
share my screen.
maybe they will.
I sent a request to do so. Okay.
Okay, I see a thumbs up. Okay, wonderful. Take it away.
Great, thank you. So my name is Selena and I'm IT, and today I'll be talking about some recent work that we've done in collaboration with June and Doug, where we've been interested in investigating this record high ozone anomaly that we observed in the Southern Hemisphere mid-latitude tropopause region and how we attributed that to the 2019 SSW. So in early 2020, there were very large chemical perturbations observed in the upper troposphere and lower stratosphere. So these plots come from MLS data, and they're zonal averages between 30 and 50 degrees south around the tropopause region. And the red line here is the 2019 to 2020 data, and the solid blue line is the average of the previous MLS data record from 2004 to 2018. And what we see is that in 2019 and 2020, both ozone and carbon monoxide are much higher than the previous annual average. And the shading here is the full range of climatology. So we see that the values are record high for both of these chemical species. And to understand what's driving these chemical anomalies, we first need to look at the context of the 2019 Southern Hemisphere, which was very anomalous because of a rare SSW that occurred in early September. So here we see the telltale signs of an SSW, which is a slowdown of the zonal winds of the polar vortex, and with that slowdown of winds, also a very sharp increase in polar cap temperature. So we see here over the course of a few days, you get a jump of over 30 Kelvin in temperature in the stratosphere. And this SSW has previously been connected to a record negative SAM. So the southern annular mode is the position of the tropospheric eddy-driven westerly jet in the southern hemisphere. When it's more poleward, it's in its positive phase. When it's more equatorward, it's in its negative phase. And we see in the SAM indices on the left that following the SSW, you have record negative SAM indices. And it's known that a negative SAM influences climate throughout the southern hemisphere. And in Australia, it influences climate, especially in the southeastern region, where you get less precipitation and hotter temperatures. And with hot and dry conditions, you can have wildfires. So indeed, in 2019 and 2020, Australia had a very severe bushfire season, and you can see that in images from the satellites as well as from the ground. And this wildfire season was very anomalous, not only because of the large area burned, but also because it was associated with a number of extreme weather events known as pyrocumulonimbus clouds or pyro-CVs. So pyro-CVs are wildfire-initiated or sustained thunderstorms that create essentially this chimney of smoke that mimics a volcanic eruption, and it can send wildfire products into the upper troposphere or even directly into the stratosphere if there's strong enough convection. And in late December of 2019 and early January of 2020, we saw a number of pyro-CVs which injected wildfire smoke directly into the stratosphere. And you can see in these satellite images on the left that that smoke is being carried in the large-scale circulation. So these pyro-CV events have been termed the Australian New Year Super Outbreak, or ANYSO. And this map is showing where those pyro-CV events occurred, all in that southeastern region of Australia, which is mostly affected by the negative SAM and the SSW. And during the super outbreak, over the course of just a week or so, it's estimated that over 1 teragram of smoke was injected directly into the stratosphere. So the motivating questions for our project was, how did these pyro-CVs influence UTLS composition and chemistry, and also whether dynamical effects of the 2019 SSW played a role in driving record high ozone? So to answer these questions, we use 2 main classes of tools. We have satellite data from MLS and ACE, and then I am running model simulations using SD-WACM, nudge to mirror 2, in the 70 level version of the model. So first, going back to that motivating ozone anomaly, this is MLS calculated anomalies. Looking at January, we see in the mid-latitude UTLS region that there is really high ozone. So we're above 3 sigma from the climatological mean. But if we look back in time, what we saw was that these ozone anomalies actually date all the way back to September of 2019. And that in September, the high ozone is actually constrained to the polar region, and the anomaly is higher up in the stratosphere, in the mid to upper stratosphere, around 30 hectopascals. And the fact that we see the anomaly in this specific region tells us that what's driving this high ozone is suppressed polar stratospheric cloud formation, because 30 hectopascals is the typical height of PSC formation, and these are the surfaces for ozone depletion. It makes sense that with an SSW, when you have much warmer polar temperatures, you're suppressing the cloud formation and you're reducing the amount of ozone that can be depleted. And if we step forward in time, we see that there's a downward propagation of this ozone-enriched air. And this makes sense because SSWs are associated with polar downward transport. And we can see that this ozone-enriched air is moving from the mid to upper stratosphere down towards the tropopause over the course of a couple of months. And once you get that ozone-enriched air near the tropopause, we see that there is more efficient meridional mixing, so that high ozone air can then influence the mid-latitudes in December and January. And this makes sense because we know that mixing barriers are stronger higher up in the stratosphere compared to in the UTLS. So we have this sort of dynamical mechanism for mid-latitude high ozone. And now I've added in plots of WACM calculated anomalies on the bottom row compared to our MLS anomalies on top. And what we see is nudging WACM to mirror to reanalysis data allows us to capture these ozone anomalies very well, both their spatial and temporal pattern. And here, this Wacom anomaly does not have any added wildfire chemistry, so it's just nudging to the winds and the temperature, and we're able to capture basically this entire pattern. So this suggests that the dynamical effects of the SSW can explain a lot of this high ozone anomaly. But if we zoom back into that region of interest, which was January in the mid-latitude UTLS, what we saw was that the model might be missing some high ozone. We see that the anomaly is much lower in the model than what's calculated in MLS. So to understand why that might be, I'll first explain the model runs a bit further. So we have three classes of runs. First, there's the climatology. These runs were done by Doug, and I'm using monthly output between 2004 and 2018 to match the MLS data record. And then we have a control run, which is the 6 months covering the Australian bushfire season. And there's no added wildfire emissions, so it's just nudged to the observed 2019 and 2020 dynamics. And if we take the difference between control and climatology, what we get are the dynamical effects, or in other words, how anomalous the dynamics were in 2019 and 2020. So we can look at some zonal averages of this dynamical effect. So here in the dash blue are the MLS calculated anomalies for CO and ozone, again, average between 30 and 50 degrees south near the tropopause. And then the solid black line is our Wacom calculated anomaly, again, with no added chemistry. So what we see is that the model in its base state is missing some chemistry in January of 2020. So we see that it doesn't capture any of the carbon monoxide anomaly, which is likely from the wildfires. And if we look at ozone on the right, we see that the model actually does a pretty good job in December of 2019. But once we get into January, we see that there's up to 10 ppb of ozone missing in the model. So then we introduce a wildfire run, which is run for the same 6-month period, but now we're adding in wildfire emissions at altitude to simulate these pyro-CBs that occurred in late December and early January. And because both the control and the wildfire runs are nudged to the same dynamics, taking the difference between them leaves us with the chemical effects of the wildfires. So I won't go into much detail about how I added these emissions, but essentially what I did was I injected carbon monoxide first into the model until I could recreate the MLS anomaly at different levels. And then I scaled emissions of other species to this CO emission based on literature-based emissions ratios. So this table here is just summarizing all the wildfire products that I ended up emitting in the model and what ratios I used to CO. And what we saw was that when we inject all of these reactive species at altitude, we're able to recreate the ozone anomaly much better. So this is the carbon monoxide, and we can see that that matches better with MLS. And for ozone, we see that we're getting that missing 5 to 10 ppb in January that dynamics alone couldn't explain. So that was a promising result. And we can also try to quantify how much of this high ozone comes from dynamics versus chemistry. And we see that dynamics plays a dominant role, around 80% of this total high ozone in January of 2020. But we can't rule out uncertainty in transport simulated in the model, even though we're nudging to dynamics. So we also wanted to see whether we could separate chemical and dynamical effects from satellite data alone. So to do this, I use tracer-tracer correlation analysis, and I'm using data from ACE here, which is really great because it measures both inert and chemically active species in the same solar occultation. So here I'm using HF as our inert stratospheric tracer, and the theory behind this is that dynamics should influence both ozone and HF in a similar manner. So you should see a correlation between them that's dynamically driven. So here I'm showing the correlation between ozone on the y-axis and HF on the x-axis. Every point here is a single solar occultation from ACE between 2004 and 2018. And you can see that they're generally correlated, and there's interannual variability in these fits, and that's what this gray shading is. And if we add in data from 2019 and 2020, we can see whether these anomalies are more dynamically or chemically driven. So we see that in October through December of 2019, that the data points are within that range of climatological variability and also are centered around the baseline fit. But if we look at January, we see that the ozone levels are elevated relative to the amount of HF and that they sit outside of that range of interannual variability. So this indicates that we do have some ozone production in January, which is consistent with our model results, where we needed to inject some wildfire emissions to explain that total ozone anomaly. So to conclude, we observed record high ozone in the southern mid-latitude UTLS and attributed that to both dynamical and chemical effects of the 2019 SSW. And we found that this dynamical effect of downward and equatorward propagation of ozone-enriched air is the dominant contributor to high mid-latitude ozone. But that being said, chemical production of ozone from pyro-CBs is still important in January of 2020. And that is everything that I have. And if there's time for questions, I'd be happy to take them. Thank you.
Thank you. Any questions? I can moderate from here because you're not going to see when people come, but Rafa.
Really nice talk. I have a question on the anomaly when you include the fires and you make the difference with the climatology. For CO, the model decreases after December or between December and January faster than what does for ozone. Do you know why? I mean, that's because it was a pulse on the emission and you should include emissions for a longer period of time of CO? Or why is that difference between CO and ozone?
That's a great question. So for my emissions, I'm only emitting on 4 days, which are known to have direct stratospheric injection of wildfire smoke. So that's December 29th through 31st and January 4th. But it was a very active wildfire season, and I think that there is more CO sort of in the UTLS region. But since I'm only adding in emissions on those 4 days, I think we're getting a faster decay than if we're representing emissions sort of in the upper troposphere as well as those 4 most extreme pyro-CB events. So this is capturing the largest events, but I think there are some smaller events later on that would help match that even better.
Thank you.
Thank you.
Okay. Thank you, Selena. There seems to be no more questions. Thank you for your talk. We move on to the next one. So we have Dai Kashin presenting on contribution of gravity waves to the lower thermospheric winter to summer meridional circulation in high resolution WAWG. This button, push forward. This is the pointer. I can see.
はい。
Okay.
Can you hear me? Okay. Thank you.
Sorry, I can put these for you.
You can show.
So you can see that you don't have to look.
That's nice.
Yeah. Okay.
Oh. I see. Thank you. Oh, thank you for the introduction. I'm Daiko Singh, and today I'll talk about the lower thermospheric circulation analyzed by the high resolution WAWG. First of all, I'll introduce the meridional circulation in the MERT region. There are several meridional circulation in the upper mesosphere and lower thermosphere and middle thermosphere. And these circulations are related to the temperature structure. And in this upper mesospheric circulation is related to the gravity wave quotient, and in this lower thermospheric circulation is mainly related to the gravity wave and tidal wave, but the driving mechanism is unclear, and there are some weak bias for lower resolution models. And WAWG is a powerful tool for analyzing this circulation for these studies. In addition, there are several tracer distribution analyses because there are some gradient of tracer species, like this is an example. So this is CO2 distribution, and there is a large vertical gradient of CO2 distribution around here, and there is a weak distribution, a weak gradient around this region. The middle thermosphere circulation is mainly driven by ion drag and diabatic heating and pressure gradient force. So there may be some different mechanisms that driving these circulations. So in this study, to analyze the origin and nature of waves driving this circulation, the dynamical process through the middle atmosphere is examined using high-resolution WAWG-X. For this study, I used the WAWG-X with the horizontal resolution with 25 kilometers, and the vertical resolution is 0.7 kilometers. And I used the data for 1 year from January to December. And in this study, I specified the small-scale disturbances, that is regarded as the gravity wave, is defined as the waves with zonal wavelength smaller than 2,000 kilometers. So this is the overall results. The left panel shows the Weber star, the meridional component of the residual mean circulation, and the right panel is the zonal mean, zonal wind, and the flux divergence. So for the meridional flow, we can see in this region, there is a southward flow in this region. And for the AP flux divergence, we can see the positive forcing in this region and negative forcing in this region. So this distribution is consistent with this circulation. So we can consider some wave-driven mechanism. In addition, I made a little more further analysis for smaller scale components. So this is the IP flux divergence and zonal mean, zonal wind. And the lower panel shows the accumulated IP flux divergence, which is accumulated from zonal wave number 1 to zonal wave number 2, 3, and all zonal wave number in this region, and also in this region. For large-scale components from wave number 1 to wave number 2, there's a large negative contribution around this for both regions. And these components correspond to the migrating tidal waves. And for small-scale waves from wave number 10 to 200 in this region, there are large contribution for the net forcing. So there is a large negative forcing in this region, and there is a large positive forcing in this region. The smallest waves are very small contribution. In addition, so I plotted the similar figure, but only using the equinox divergence due to the waves smaller than 2,000 kilometers. So it is also consistent. So we can see negative forcing here and positive forcing here. So almost all of this structure is explained by this structure. In addition, I checked the momentum flux divergence only. So this is the vertical component of the EP flux divergence. So it is also similar. So we can analyze more further for the vertical component of the momentum flux. So here shows the vertical momentum flux divergence, and I also checked the seasonal variation. So this figure shows the 1 year distribution and time and latitude distribution of Weber star and wave forcing for due to the small scale wave in this altitude region from 115 to 120 kilometers. So we can see the southward flow in this season and also in this season. And in this season, we can see northward flow. And this distribution is consistent with the wave forcing. So we can see positive wave forcing in here, and also here. And the negative forcing observed here, and here, and here. So this distribution of the forcing is consistent with the circulation. Then I checked the phase speed distribution. So the right panel shows the momentum flux as a function of phase speed and altitude. It is derived by the 2D FFT. So the color indicates the U prime W prime bar, and the white contour indicates the wave forcing, and black curves are the zonal wind. So U prime W prime bar is positive for eastward waves and negative for westward waves. That indicates the upward propagation of gravity waves. And we can also see that there is the slow westward wave. In this region, the westward waves are dissipated in this region and makes the westward negative forcing. This negative forcing corresponds to the negative forcing here. And for eastward waves, we can see large positive forcing that corresponds to the positive forcing here. In addition, we can see that the waves slower than the zonal mean, zonal wind is also dominant in this region. But these waves cannot propagate from below. So I checked where these waves are coming from. So here shows the vertical energy flux. The sign of vertical wave energy flux corresponds to the wave propagation. So the positive region indicates the upward wave propagation, and the negative region indicates the downward wave propagation. So we can see very clear contrast at here around 67 kilometers. That indicates the divergence of eastward waves around here, and also for the fast westward waves. So these waves are diverge around this region. On the other hand, for slower westward waves, this value is positive over all altitudes. So these waves are propagated from the stratosphere, like here. But for this region and this region, there is a divergence of waves at this altitude. So I also checked the horizontal distribution, so latitude, height distribution of U prime phi prime bar for eastward waves and westward waves decision. For eastward waves, we can also see there is a large clear divergence at this altitude. As a contour is zonal mean, and the color is U double prime phi prime bar. So we can see there is a very clear divergence at this altitude over wide longitude. Although it is not so clear for westward components because the westward waves are generated more low altitude. So the question is it possible to estimate this wave generation from the mesospheric jet structure, but because it looks related to the structure of zonal wind. So I checked the absolute horizontal temperature gradient. Here shows the temperature gradient at the same latitude region. This value generally increases with the altitude, and we can see large value in the above the zonal wind maximum. And the zonal variation, there is a maximum here, and maximum around here, looks associated with the jet structure. So zonal wind is also large, strong here, and here, and here. So it looks related. These results indicate the wave generation can be estimated from the structure. So I also checked the seasonal variation. So here shows the U prime W prime bar in the lower thermosphere for January, November, June, July, and the lower panel shows the temperature gradient in the mesosphere in the same season. So these comparison is a monthly variation, and these are the comparison for seasonal variation. We can see some seasonal variation because we can see large positive U prime W prime bar in the winter high latitude here and here in the lower thermosphere. It is consistent with the large temperature gradient around this region and this region. In addition to the seasonal variation, we can see some monthly variation. That is large positive U prime W momentum flux here, but it moved to eastward here, and the maximum, it is not so clear from this figure, but yeah, the maximum was here, and also here, and here, and here. So this distribution is consistent with the pattern of large temperature gradient region. So temperature gradient indicates the wave generation region. So this is the conclusion. The mechanism driving the lower thermospheric circulation is examined. In the winter hemisphere, the generation of eastward gravity waves from the strong westerly jet is important. The characteristic is different from westward waves because westward waves are propagated from lower heights and dissipate in the upper hemisphere that contribute to the mesospheric circulation. In addition, the gravity wave generation in the mesosphere could be estimated from the temperature gradient. That may contribute to the improvement of the parameterization. That's all. Thank you. Any question?
So is there a difference between the July and the January? Two different solstices?
Yeah, I also checked the result for January. I compared the result for January and July, and the difference is not so large. Yeah, although the north and south side is opposite, but they are similar mechanisms.
Okay, this circulation is a meridional circulation in the lower hemisphere. Which season is stronger?
Sorry. Go ahead.
Yes, this circulation, which July is stronger or January is stronger?
I think I compared I don't have, sorry, I don't have the figure. Yeah, I compared the result for January and July, but the difference is not so large. Yeah. I will show the figure after that.
Okay, it's okay. All right, okay, is this one?
No. I don't have the figure now, but I will show the figure
Okay.
later.
Okay, let's see. So basically, your diagnosis reveal that it's mostly from the gravity wave, not the tides.
In this region, in winter lower atmosphere, the driving mechanism is mainly explained by the gravity waves. In the summer hemisphere, there are some contribution from tidal wave.
So the winter hemisphere is mostly from gravity wave, but the summer hemisphere from tides as well. Also
That's
tides
right. I think so.
Okay, all right. Is this paper, have a paper published, like a citation?
It will be submitted soon.
Okay, all right. Okay, thanks.
Thank you. No? Thank you.
Okay, thank you for everybody for being perfectly on time. Next, we have Susan Nussel about WACMX studies of the thermospheric hydrogen response to solar activity and to impacts on greenhouse gases across atmospheric regions. Okay, you're online and can share.
One moment, please. You able to see?
Yes, we can see fine. Thank you.
Okay.
You can go ahead.
Thank you very much, and good afternoon, everyone. Today we'll be discussing the whole atmosphere studies with WACMX to investigate the response of thermospheric hydrogen to solar activity, which is a major source of natural variability in the upper atmosphere, as well as the impacts of greenhouse gases across atmospheric regions. And I'll be discussing the WACMX simulations and their comparisons to observations from the Wisconsin Mid-Latitude Northern Hemisphere Multi-Decadal Hydrogen Air Glow emission data set. Many people have contributed to this work, and thank them for their contributions to both the observational and modeling aspects of the work. Okay, so atomic hydrogen forms the upper boundary for atmospheric processes involving hydrogen-containing constituents at lower altitudes, and these include methane, which is one of the most important greenhouse gases increasing due to human activities. Hence, hydrogen can potentially serve as a fingerprint of climate change processes. Additionally, atomic hydrogen is important to the understanding of space weather processes, neutral atmosphere plasmasphere coupling processes, and non-Maxwellian physics present in the exosphere. And methane reduction is really a major source of focus now in the global community for climate mitigation due to the fact that methane has a larger radiative effect per molecule and a shorter lifetime in the atmosphere of about a decade, and also an acceleration in growth rate compared to carbon dioxide. And there have been a number of talks throughout the meeting about methane. So methane is a major source of hydrogen-containing species in the middle and upper atmosphere. And one of the primary reasons for this is that at the top of the cold troposphere, much of the water vapor from the lower atmosphere is frozen out at this boundary. However, methane can transit into the stratosphere in the middle atmosphere. Chemical and photolysis reactions in the middle and upper atmosphere eventually break down methane into other hydrogen-containing species, which eventually becomes exospheric atomic hydrogen. So simulation results also indicate that carbon dioxide cooling in the upper atmosphere leads to increases in methane in the, in atomic hydrogen in the upper thermosphere. This differs from the total, the decrease in the total neutral density that is associated with atmospheric contraction and increases in carbon dioxide cooling. Additionally, in order to understand impacts of greenhouse gases, it's important also to understand and include the understanding of natural variability, such as the 11-year solar cycle, which is a major source of natural variation in the upper atmosphere and also impacts the hydrogen density. So the work that I'm presenting today involves analysis of WACMX simulations run for the seminal studies by Solomon et al., in which the seminal studies by Solomon et al. That were used to produce the first whole atmosphere simulations with a single atmospheric model of the warming in the lower atmosphere and the larger magnitude cooling in the upper atmosphere. So these simulations were run for perpetual solar conditions in order to separate, and over a 30-year period of time. And the perpetual solar conditions were run in order to separate out effects from greenhouse gases from changes in solar activity. So we analyzed these simulation results for hydrogen, and we're presenting here global averaged results for solar maximum and solar minimum in the upper thermosphere. This simulation was run with 5 years from the 1970s, which are in the blue-green colors, and 5 years from the 2000s, which are in the red-orange colors. What we see here is that a couple of things. One is that the densities, in terms of the solar cycle effects, the densities are higher at solar minimum compared with solar maximum. And over this 30-year period of time, this effect is greater than due to greenhouse gases. But also for both solar maximum and solar minimum, the densities are higher with the later years that correspond to increases in greenhouse gases. And this is due to increases in source species for hydrogen from methane and due to carbon dioxide cooling. The hydrogen response to greenhouse gases is greater during solar minimum, which is consistent with greater carbon dioxide cooling during minimum times as well. Okay, this slide shows the WACMX simulations of thermospheric hydrogen density profiles near the Pine Bluff, Wisconsin Observatory. And what we're doing here is, what I'm going to talk about next is comparisons with observations using forward modeling. So here we again show the, we're showing the simulation results. We're showing the 5 years in the 1970s and the 5 years in the 2000s for both solar minimum and maximum. And the black curves are the averages of each 5-year grouping. What we see here is that in the upper thermosphere, at this location in the model, there are higher densities during solar min than max, and also that the hydrogen response, the top right-hand panel, the hydrogen response to greenhouse gases in terms of absolute magnitude is larger at solar minimum than at solar maximum. And note that the scales are different from the solar min and solar max zoomed in figures. Furthermore, there is a crossover point in the lower thermosphere around 155 kilometers, or lower, I should say, in the thermosphere. And this crossover point below this, the densities are actually higher during solar max than min in terms of the simulations. So This figure, the figure on the right shows the zoomed in view of that crossover point. And then the figure to the left shows the hydrogen density profile extended to exospheric altitudes using the Bishop analytic model, analytic exosphere model. In the figure to the left, what we see is the darker lines are thicker lines correspond to the WACM-X thermosphere conditions that are inputted, sorry, thermospheric hydrogen conditions, and then the thinner lines are the extensions. What we see here are that there are two crossover points at above about 10,000 kilometers. Hydrogen densities are higher at solar maximum, and below about 155 kilometers, hydrogen densities are also lower at about solar maximum. However, in between, the hydrogen density is higher at solar min than at solar max. So what we're doing next is to input these, these profiles are used in order to input it into a radiative transfer code that calculates intensities that one might expect to observe from the ground. And with a Fabry-Perot spectrometer. And this instrument, the figure on the left is a figure of observations that of hydrogen Balmer alpha air glow column emission observations observed by the Wisconsin H alpha mapper Fabry-Perot when it was located at the Kitt Peak Observatory in Tucson, Arizona. And what we see here is that this is a subset of observations, and I should say here that they're plotted versus shadow height because the emission is excited by excited by solar radiation. So above the shadow, the hydrogen atoms are excited directly to higher energy states, but below the shadow, can be excited by multiple scattering. And what we see here, the red curve is intensities during solar maximum. So we see higher intensities during solar maximum than during solar minimum. This is also the case in the calculated intensities, in which we see higher intensities during solar maximum than in solar minimum. And this is a form of, this is a qualitative comparison that adds to model validation. Okay. This next plot shows solar max and min, but for the lower calculated intensities, but for the lower shadow altitude range. And what we see here is that actually, in addition to what we saw in the last figure, but what we see here is that the higher calculated intensities for the later years, the 2000s, when the greenhouse gas concentrations were higher, are higher at solar. The difference between the 2000s and the 1970s is larger during solar maximum than at solar minimum. This is due to and also that the intensities again are higher at solar max and min. This is likely due to contributing factors being that the emissions depend on the column of hydrogen densities, and also that there's a changing solar Lyman beta excitation flux over the course of the solar cycle. The figure to the right shows the same calculated intensities, but for a unit solar flux, so that we can separate out the effect from the column density, integrated column density from that due to the solar excitation flux. So this is a figure of showing a merged northern hemisphere data set of column emission intensities and at mid-range shadow altitudes, and these data have been binned, and therefore December time scales And also, one more thing is that all the observations are calibrated with astronomical nebular sources, helping to reduce uncertainties in merging of observations. And they suggest an increase between the 1990 solar maximum period and the 2000 solar maximum period that's not been accounted for by uncertainties due to experimental factors. And so what this increase is actually larger than would be expected from the WACMX simulations, and certainly more data would be needed for any attribution. We are looking forward to more data to add to this data set because one of the instruments is moving back to Wisconsin, or is moved in Wisconsin, but we'll be taking data from Wisconsin. So a couple of conclusions are that the thermospheric density rises with increases in greenhouse gases. The thermospheric hydrogen density rises with increases in greenhouse gases, unlike the total neutral density, which decreases with carbon dioxide cooling. The mechanisms are that methane increases as source species for hydrogen, and carbon dioxide cooling also contributed to the increase in hydrogen, as evidenced by the differences in response at solar min and max to greenhouse gases. There's a large solar cycle variation with the density being higher at solar minimum. I just say here, just jump to one more conclusion so I can end, which is that the possible signatures of greenhouse gases, as we think about observations more broadly, might be more apparent in situ measurements of hydrogen in the upper thermosphere at one particular altitude during solar minimum, whereas for ground-based remote sensing of hydrogen column emissions, it would be during solar maximum that we might, the WACMX simulations are suggesting we might see a larger signal in the observations. And I'm going to skip this slide just to say that one of the goals of this work is to contribute toward whole atmosphere pattern studies of climate change impacts on hydrogen-containing species across atmospheric regions. And we welcome collaborations with people studying methane, water vapor, and other hydrogen-containing constituents at different altitudes. Thank you very much.
Thank you, Susan. Okay, we have time for a very brief question, if there's any. But there don't seem to be, so thank you again, Susan. And we can move on to the last talk before break. So we have Joe. Sorry, Joe, I don't know how to pronounce her surname, I'll be honest. Seasonal changes in the thermosphere from WACMX filter 21st century projections.
I'll say it so that you can remember.
Yes, please.
Okay, I'm Joe McInerney. I work here at INCAR at the High Altitude Observatory, and Susan, who just spoke, has been working with me, along with Li Ying Chen, also in HAO, on looking at these simulations for the 21st century. So these are just, what we're going to do is look at more seasonal changes, which actually looked a little bit at the annual changes. And so the motivation for this is pretty simple. CAM and WACM are always doing, for years, have been doing fully coupled model projections as part of CMIPS and the IPCC effort. And we tried this with WACMX. We did a fully coupled projection through the 21st century, but the tuning was very time consuming and challenging. So to do the projections we wanted to do here, we decided to just go ahead with a idealized WACM projection scenario, and this is what that is. We use a FX HIST comp set, and we did 4 continuous simulations from 2020 to 2120 using these 4 IPCC scenarios. And we output monthly means and then use those to derive seasonal means, which is a lot of what I'll talk about here. To make things simpler in the thermosphere, using solar minimum quiet conditions and fixed geomagnetic field help a lot to be able to look at the effects of greenhouse gases on the upper atmosphere. this same configuration was used for for some hindcast time slice simulations, similar to what Susan was showing from Stan's work. And we did the same thing. We did it from the 1920s to the 2010s, and we published these results last year. And this is just the neutral temperature changing throughout the 20th century and in the beginning of the 21st century in the 400 kilometers up in the thermosphere. And so these results look pretty good, so we decided to go ahead and do some projections with this same type of idealized WACMX setup. There were some projections done before with WACMX by a group in the UK. Matthew Brown did some simulations and published in 2021, but he did decadal, kind of similar to what we did for the 20th century. He did it for 4 different IPCC scenarios. And then Ingrid did a projection for the SSP 245 scenario, but she only went to 2070. So we decided to build on that. And we did yearly output and actually monthly output for these 4 IPCC scenarios. And these are the forcings. This is the carbon dioxide on the left and the methane on the right. And you can see what you'd expect, that the CO2 increases more with the higher emission scenarios, the 585 being the highest. But methane actually has a different character to it. It actually turns around and actually decreases in all 4 scenarios sometime in the 21st century. So here's some results. This is neutral temperature. This is the time series from 2020 to 2120 for 4 seasons, equinox and solstice. And so what you see here is season doesn't make much of a difference from one scenario to the next. They look pretty similar and kind of remind you of like the reverse of the carbon dioxide. Here's the same thing, and this is for the ratio of atomic oxygen to molecular nitrogen. And this is something that's is useful in the thermosphere, ionosphere, and kind of resembles neutral density with the way it changes. Here you can see all 4 seasons are somewhat similar. The higher emission scenarios are actually closer together than they were for the temperature, with the lower emission scenarios kind of spread out more. And you see a little more variability as you go through toward the end of the simulation and the solstice simulations. This is for atomic hydrogen. This is kind of overlapping with what Susan was talking about. And these are also time series. And as she mentioned, the atomic hydrogen increases as a response to greenhouse gas emission increases. And you can see here, similar to the O to N2, the higher emission scenarios are closer together and the lower emission scenarios are more spread out. Here, the 585 scenario is increasing more until you get to the latter part of the 21st century, and then it kind of flattens out, and the 370 becomes the larger increasing scenario. And this is kind of goes back to what I said about methane. That methane kind of turns around, and you can see that especially in the 585, where it starts to turn around and flatten out toward the end of the simulation. So this is another representation of that O to N2 ratio. And one of the things that's interesting to look at is the seasonal change, the seasonal variation of O to N2. The left is the first 5 years of this simulation for each scenario, and they all pretty much are very similar at the beginning. And then if you go to the end, the last 5 years of each simulation, you can see it looks kind of like the time series, where you get the higher emission scenarios kind of grouped together and then more spread out for the lower emissions. And if you look closely, you can kind of see, go back. If you look closely, you can see kind of a progression of this peak and this peak becoming lower. So, and then over here you can see the same thing. This peak here increases as you go. So as you go to higher scenarios, you can see the seasonality kind of go earlier into the year. This is a different representation. This is vertical differences, vertical profile differences. This is pressure over here, and this is temperature differences in Kelvin here on the x-axis for the 4 seasons. And the thing to notice here is that they all have cooling, stronger, more cooling in the equinox time periods, less so at solstice, and that the least cooling seems to be at the June solstice. Here's the same thing for atomic hydrogen. Atomic hydrogen has a characteristic where the increasing greenhouse gas emissions actually cause a decrease in atomic hydrogen at these lower levels in the thermosphere. This is starting at 100 kilometers. And so you can see in all 4 cases, you get this increase up in the thermosphere, and you get this decrease down in the lower thermosphere. The interesting thing here is, again, the June solstice appears to be a little bit less of an increase than the other seasons. Here's lat-long differences. These are differences, take differences between 2120 and subtract off 2020. This is an annual for the whole year. Oops. And you can see mostly cooling, larger cooling is in the low latitudes with less cooling at high latitudes. Here's what the different seasons look like for temperature. And you can see that in March you get less cooling at high northern latitudes and more cooling everywhere else. But in the September equinox, you get more cooling at the high southern latitudes with more cooling. The solstice looks more like the annual changes where you get more cooling at these lower latitudes. And again, it becomes more clear here that the June temperature, as we saw in hydrogen, the June temperature seems to have less of a change than the other seasons. Here's the same thing for atomic hydrogen, and this is where we're overlapping with what Susan was talking about. This is a percent change for the time period of the simulation. Looks a lot like temperature. You get the biggest changes here in the low latitudes and less so at high latitudes. There's a little indication here of a little bit larger increase in atomic hydrogen in the southern and high latitudes. Here's what the different seasons look like. Again, like temperature, you get less of an increase at high northern latitudes than you do get for the rest of the latitudes in March equinox. At September equinox, it kind of flips around and less of an increase at the high southern latitudes. And again, the largest change here largest increase here is at low latitudes. And again, the June solstice has the smallest percent increase during the simulation. You see a little bit of a indication here that you don't really see as much on the annual plot, that you actually have more cooling at low latitudes here during solstice, a little bit here, and the increase in hydrogen higher at low latitudes, southern latitudes here, high southern latitudes here, and a little bit of an indication of that higher increase in the June solstice. So that's it. That's the changes that we saw for seasonal. For temperature, we see that the time series are very similar for all the seasons. We get relatively more global cooling at equinox than we do at solstice, and with the June solstice having the least amount of cooling of the 4 seasons. There's a clear geographic dependency of cooling when you look at the latitude, longitude plots, and each season is different. For the OLN2, the variability increases for solstices as you go through the simulation, and you don't see this in the equinox, but you see it in the solstice. The seasonality is shifting earlier in the year when you go to higher emission scenarios. You get a smaller change between the 2 high emission scenarios than you do for the lower emission scenarios. And for atomic hydrogen, earlier decrease in solstice during the 21st century. And you can see that that's due to this methane reversal. As Susan mentioned, atomic hydrogen has a dependence not just on what happens with lower atmosphere carbon dioxide, but also methane. And you can see in the forcing figures that comes through with the changes here in the hydrogen, that they actually turn around as you go through the simulation. June solstice has smaller increases, which is similar to less cooling in June solstice for the temperature. And there's, again, this geographic dependency, different seasons like we saw in temperature, and it's fairly similar to temperature. From here, we're going to do something we've been wanting to do for a while, which is compare with the UK simulations that they've done. We should get something pretty close. It's a good sanity check, because they used a pretty similar version of WACM-X. Then we need to work on getting a publication kind of describing the simulation changes, annual changes, and some of these seasonal changes. And then hopefully, when we get CESM3 with WACM-X7, we can attempt a fully coupled projection and maybe have better luck doing the tuning, maybe with less effort, or maybe with a little help from some of the lower atmosphere people. That's it.
So Joe, so both Susan and in Susan and your simulation, you see a hydrogen increase over the time, and so both the CO2 and the methane, CO2 increase and methane increase, can cause a change in hydrogen increase, right? Do you know which one is more dominant forcing between these two?
I know for sure we can clearly see, as you saw in the time series plots, that you can see when methane starts to turn over, especially in the highest, the 585. When you see methane start to turn over there, you see a little bit of a delay when the 585 starts to turn over. So clearly, I think CO2 is a little trickier. I think CO2 will require some different representations of the data, but here you can clearly see that it's not just CO2 causing the changes in atomic hydrogen, that methane does have an effect, and it's a clear effect, even up at 400 kilometers from the methane at the surface. So yeah, maybe that's something we can
Yeah, that would be very interesting to find out, contribution from these two forcing.
I think for publishing, we definitely need to make some comment on that, so, yeah.
Okay,
so
thank
you can
you.
help me.
So we'll reconvene at 3 p.m. for the last part.
First talk will be given by Daniele Visioni, recent updates on representing large volcanic eruptions in CESM. You have that.
Yep. I guess I can. Okay. Okay. Hi, everyone. Volcanic eruptions in general, not just large. Mainly volcanic eruptions in general, not just large. Mainly this is work that Ilaria and Simone have been doing. Ilaria mainly, all of the analyses are hers, most of them. But she's at the Hunga Tonga meeting up at the Mesa Lab, so I've been presenting. Well, why study large volcanic eruptions? Well, I always like to go with this quote by G. Manson in 1992 that they are one of the best acid tests for climate models. This was after Pinatubo. We know that they cool the planet after they happen. They help us understand how models perform. They're a great experiment. And I think that they represent one of the best and coolest cases of stratospheric surface coupling because they include dynamics of the stratosphere, chemistry, microphysics, climate sensitivity. And then lastly, of course, because studying them can also provide insight about the impacts of things like stratospheric aerosol intervention and climate intervention strategies. So studying them can be a good test bed to understand the uncertainties that are related to some of those proposals. But actually studying and modeling these volcanic eruptions is pretty challenging, right? The one we always go to is Pinatubo. So these are results from the ISA MIP, the Interactive Stratospheric Aerosol MIP that was run in 2021, 2022. These are some of the high-level results. If you try to simulate the eruption of Pinatubo in the same way in all the models, you get pretty different results when it comes to surface area density. So here's an example of both overall in the tropics, the surface area density, and this is at Laramie. So you can see that there are clearly large differences between the models. Why are there these differences? Many different things, resolution, dynamics, the different microphysics, most of all. And also, and I think this is an important thing, and I'll get back to that, there's also pretty much a large uncertainty over how to actually even start the eruption, as in what was the height and the magnitude of the injection. This was true for Pinatubo, where the estimates of the amount vary, and also do you start the eruption right at the day where it happened, or do you let it spread a bit? So actually this was another part of the ISME protocol, which was sort of trying to inject at different altitudes or different amounts and trying to figure out what the differences were. So when trying to do model intercomparisons in this case, it gets pretty hard to understand what exactly is the source of the differences one observes. And lastly, the available observations, even for things like Pinatubo, they were very large, but it was now more than 30 years ago, are pretty poor and saturated in many cases, right? Here you can see some examples for surface area density. You can see, first of all, the gaps, even for effective radius. First, sulfate burden is sort of pretty poor in many of the ways it's estimated. So there are also challenges in what exactly are we comparing against? Okay. In CSM, with WAWG, been doing volcanic eruptions for a long while. This is a paper done by Anja Schmidt and Mike Mills back in 2018, essentially looking at not just Pinatubo, but a lot of volcanic eruptions starting in the 1980s all the way to 2014, so both large and small, not just looking at the stratospheric aerosols, but also then at the effective radius, at the effective radiative forcing, essentially trying to understand what is actually the magnitude, the forcing produced by the volcanic eruptions. This was done with CSM1 and with MAM, so with model aerosol microphysics. Then in CSM has continued doing interactive volcanic eruptions, so starting from the injection of SO2 also for CMIP6. This was from the paper was led by Nick Davis. Essentially, CSM was the only model in CMIP6 that had interactive stratospheric aerosols and interactive volcanic eruptions. Every other model, UKSM did some runs like this, but then they never published them, so every other model used the prescribed aerosols. So CSM was the only one. The other thing we know, again, the microphysics, so how the actual aerosol size distribution is represented is pretty important. So these was some results from Simone's paper from last year. Normally the simulations done with CSM up to now had been done with this model aerosol microphysics 4. Those are the log normal curves that you see here. Well, what you can see here, based also on the balloon observations that we have, is that model aerosol microphysics, MAM, it's fast, it works well, but it's not perfect, right? It's a trade-off between speed and accuracy. The other way, the more complex, computationally speaking way to represent the aerosols is through sectional aerosol microphysics. So this is what, this is Karma. This is, again, from Simone's paper. You can see these first simulations of Pinatubo using Karma, and you can see how they do represent, Karma does represent the size distribution quite a lot better, especially for the largest particles, right? And the issue here is that, well, these particles are exactly the one that sort of are the most efficient at reflecting sunlight, so they are quite important for forcing. So if MAM doesn't capture them properly, that's kind of a problem. So the inclusion of Karma in CSM2 could be one way to improve the accuracy of simulations of volcanic eruptions. Fundamentally now here, these analyses have extended Simone's earlier results, showing not just the results for the Pinatubo eruption, which is the largest one, but also for the same kind of eruptions that Anja Schmidt considered back in 2018, so all the way from 1980s, sort of looking at overall 29 small to moderate and large volcanic eruptions using an SO2 data set. in the 2-degree version of CSM2 using both MAM and karma so that we can compare what are the actual differences between them. Just as a note, this is the difference in computation cost. So karma is 8 times more expensive for the 2 degrees version than MAM. So that's, again, one other thing to keep in mind when thinking about this. And this is 3 ensemble members. Those are the simulations that have been done with fixed SSTs. The thing that we've tried to do is sort of to separate the analysis between the 3 different periods, looking at Pinatubo as its own thing, because there was a large volcanic eruptions, again, around 10, 12 teragrams of SO2. The period, especially between 1999 and 2005, when there were almost no volcanic eruptions, or very tiny ones, and then periods with more small volcanic eruptions. First thing to note here, there seems to be like both MAM and karma are representing an eruption that actually the available observations don't seem to observe. When we've looked into this, it looks like the database for these eruptions assumes a much higher altitude for these 2 eruptions that happen here than other data sets. So probably that's another issue, right? This is not the model being wrong, is the initial condition, is the boundary condition for the eruptions being potentially differently estimated. So again, when observing these differences, it's important to keep that in mind as well. But you can see here for Pinatubo, there's probably the largest difference between MAM and karma, where in terms of lifetime, or in terms of the e-folding time over the cloud disperses. So we've tried to look at these again in a way more systematic by looking at what happens in large and smaller volcanic eruptions, and we found some pretty interesting thing. So these that we had that showing up here is sort of the efficacy. Given the amount of SO2 injected that is the same in both runs, what's the AOD that you produce? And the interesting thing to see is that when it comes to the 2 largest volcanic eruptions, El Chichon and Pinatubo, the efficacy converges to the same number for both things. To me, this is a suggestion of the fact that fundamentally both MAM and karma are somewhat tuned to have this efficacy for the eruptions that are the most studied. But then there is a 20 to 30% difference in the efficacy when it comes to other kind of volcanic eruptions. So, and you can see here how MAM, so in these other plots, you can see we have sort of the temporal dots and for each latitude of this difference between burden and AOD, and how essentially MAM always has the same efficacy independently of the eruption size, while karma does change its eruption quite a lot. And we know the interesting thing is that we are starting to see some studies and observation of the fact that during small volcanic eruptions, actually the size distribution does not increases in general, but might even decrease. And so it's interesting to see how clearly karma does see this difference between large and small volcanic eruptions in terms of efficacy. So indeed, this is the same. This is the plot for effective radius. You can see how MAM sees a larger effective radius in general, but while the Pinatubo effective radius is pretty well reproduced, there are plenty of volcanic eruptions where both MAM and karma do or both overestimate the effective radius. So the other results in the literature kind of point to the fact that these is clearly expected and that the behavior of karma and MAM in both cases is wrong, which has some interesting implications. Of course, then at that point, if you see the match, the top of atmosphere radiative forcing match, it does look pretty good in both cases. There's also other analysis that Ilaria has done with looking at the double radiation cold that show that MAM actually is a stronger direct forcing. But this is an interesting thing, of course, because again, you might have different size distributions or AOD, but still have a good match of the forcing depending on how well you're sort of tuning some of your parameters. So just as a conclusion, first of all, these will be available to study, and I think it's quite a good, interesting thing to have these 30 years of different kind of eruptions to analyze a bit more in depth. Karma is clearly more resolved, a more computationally expensive method, and it does capture aerosol evolution much better, right? All of the processes that happen exactly at the sizes where these matter is pretty important. And there are some indications that it does perform marginally better over a set of metrics when we're thinking about generic ways to understand how well are the models reproducing volcanic eruption. So this is, well, an example for some metrics that we're sort of working on. And Karma does show that, as in general, it has much better metrics when it comes to sulfate burden than MEM does. But they do pretty similarly in terms of effective radius and AOD. Yeah, and the next steps, definitely hope to maybe include sort of produce simulations of SAI, or stratospheric aerosol injection with Karma, and trying to understand the differences between Karma and MEM in these, and then what is the ultimate impact on surface climate as a way to represent the stratospheric aerosol uncertainties. That's all I have. Thank you.
So for the large eruptions like El Chuchana and Mount Pinatubo, the observations were not as robust back then as they are today. So you're also limited by that, right? To know how well these models, these surface area density models are working.
Yeah, that's exactly the point. So for instance, in this set of metrics that we're working on, we have tried to integrate all of these uncertainties over the observation. And the thing in a way, hopefully is gonna be different in CMIP7 is that CSM being the only model that ran all of this historical period with that means that we don't really have another model to compare all of these with. And this is hopefully gonna change for new eruptions. But the new eruptions are also all small. So there's this balance where we don't have a large one where we have better observation, and we're not gonna have, if you see Ross Salawich's paper, we're actually been degrading our capacities to look at stratospheric aerosols and stratosphere over time. So I don't think that a new Pinatubo, we would get necessarily better observations than we did in 1992. Okay,
so I know nothing about this, but I have a question. Why is it always Pinatubo and never any, did you ever study the eruption of Eyjafjallajökull in Iceland? Because I know there was quite extensive observations from DLR. They even sent the aircraft there and had in situ measurements.
So, so the problem with the answer why Pinatubo is just because if you want to look at the surface climate impact, Pinatubo is the only one that has signal to noise ratio that allows you to do that. It's also tropical, unlike Asia, which is sort of higher up. Plus, a lot of the observations of a lot of satellite observation were messed up by the fact that the cloud cover was pretty high. So in that case, to look at some of the sulfate properties was actually not that easy for that one. So the one now of interest, this Ruang that happened last year, that is a quarter of a teragram, that is interesting. There's some of those sort of people have been looking now at La Soufrière that happened also in like 2018. So there are new ones, but actually not being as big, for instance, we don't have as much data, comprehensive data that we do that for Pinatubo. So.
Very quick. I've basically also, related question. Have you thought about Hanga-Tanga, and can you make a recommendation, MAM4 versus Karma for Hanga-Tanga?
Well, yeah. So they're hashing it out at the Mesa Lab right now, right? And so there's a lot going on in there. Although I think. Yeah, so we're soon going to have results there in terms of both MAM and Karma in that case. Maybe Simone wants to say something. I don't know. She has her hand up, and she's been doing some of that.
Well, first of all, I want to not give the impression that MEM gives us the wrong forcing. Actually, for CMIP7 with the new data set. The reason why it is different here is because we ran Karma and MEM with the exact same injections, and so we get a larger burden. What we usually do for MEM is to compensate for that, since MEM doesn't get the high sizes like you showed nicely, we increase the mass, or we have more mass in MEM, and we inject less mass for Karma, so we get the same forcing for a CMIP simulation, right? But here, this study is really to do, when you inject the same mass what will happen. But as you see here, even if we inject the same mass, the forcing is very little. But the heating, for example, some things are less good with MAME, but that's what we try. Even though we run MAME, we want to get a good climate. I just want to give not the wrong impression that MAME isn't good when we run it in CMIP7.
Oh no, actually, I wanted to say the opposite, which is I think that the trade-off in computation still shows that there are a lot of good reasons to still go. I am totally convinced that there's still way good reasons to have my model.
And with Hunga Tonga, it's the same thing. We play games on how to inject to get the best outcome with Karma and MAME. Karma has a better size distribution, obviously, so it's more physical to run. But I don't
to
know.
me, the injection parameter is a tuning parameter in a way, and so doesn't necessarily tell you anything about how good the aerosol representative it is, because you tune it to get the best results. So the ISOMIP results were to make sure that you get the same thing, but in that case, you don't know what is right or wrong. So it's very intricate in terms of understanding who's giving you the better representation. Yeah. Okay. Yeah. Sorry.
So next presentation is given by Walker Lee, and it's on the pre-industrial and 21st century response to climate intervention with stratosphere aerosols in CESM2 WACM 6. Do you know how this works? Okay.
Wonderful. Thank you very much. Indeed, I'm going to be talking about some climate intervention simulations from the past and present that we've run using CESM2 WACM 6. So many people in this room have probably at least heard the term climate intervention before. It refers to a family of technologies which could be designed to reduce some of the impacts of global warming in the event that carbon emissions and concentrations are in the atmosphere are not reduced in a sufficiently timely manner. The term climate intervention has been known by a variety of names over the years, including geoengineering, solar radiation management. There are several families of climate intervention proposed technologies. The one that I'm going to be talking about today is stratospheric aerosol injection, where artificially increasing the stratospheric aerosol layer to reflect sunlight could potentially cool the planet and reduce some impacts of global warming. There have been several prominent simulations of stratospheric aerosol injection using CESM2 WACM, and I'm going to focus on two of them today. The ARISE SAI 1.5 protocol, that's an experiment that some of you in this room may be familiar with, and then the G6 1.5K SAI protocol. That's a GeoMIP, Geoengineering Model Intercomparison Project experiment that was proposed last year and is currently in progress. Both of these protocols follow the same fundamental structure, where they use the SSP to 4.5 moderate warming scenario. We define some reference period, which for both of these sets of simulations corresponds to the 2020 to 2039 average under the SSP 4.5 scenario. And then beginning in the year 2035, we use stratospheric aerosol injection to offset that excess warming over and above the warming in that reference climate throughout the experimental period. So the main differences between these two experiments is where and how we choose to inject stratospheric aerosols. The ARISE SAI 1.5 protocol has us inject at 4 different locations in the subtropics, 30 degrees and 15 degrees north and south. And the reason why we inject at these 4 latitudes is so that we can adjust the injection amounts independently in order to not only manage the global mean temperature, which we're abbreviating T0, but also regional temperature patterns. T1 refers to the interhemispheric temperature gradient, and T2 refers to the equator to pole temperature gradient. Basically, in addition to managing the global mean, we're managing the balance of surface temperatures between the 2 hemispheres and Arctic amplification. In contrast, the G6 experiment is a simpler injection strategy. We're only injecting at 30 degrees north and 30 south, and the injection is going to be done in equal amounts, and we're only controlling for global mean temperature. And this simpler injection protocol allows for, at least in my opinion, an easier comparison of responses to stratospheric aerosol injection across multiple models. looking at some of the surface climate impacts of these experiments, the map on the left is results from the ARISE protocol, and results on the right are results from the G6 protocol. And we can see that by injecting the same amount in both hemispheres, in CESM2 WACM6, hemispherically symmetric injection overcools the northern hemisphere and undercools the southern hemisphere relative to the baseline. However, in the ARISE SAI 1.5 protocol, because we are allowed to choose our injection rates at the different latitudes independently, we can choose to inject more in the southern hemisphere in order to not have this response. And so in ARISE SAI 1.5, most of the injection split across the 4 latitudes goes in at the 15 degrees south injection site. However, in both of these experiments, by the end of the simulations, we have this cooling patch just south of Greenland, which represents a decline of AMOC, the Atlantic Meridional Overturning Circulation. And this demonstrates that the injection strategies that we're simulating here, at least in the time frame that we are simulating, are not sufficient to slow or reverse the decline of AMOC just by cooling the surface. And this is one of the questions that is going to drive the main experiment that I'm going to talk about today, which we're currently working on. SAI simulations are often short, and the background, they're often simulated against a global warming background because that's the scenario in which SAI would be deployed. And so therefore, it can be difficult to separate the changes to the surface climate, which are a result of the SAI, or a result of the background changes due to global warming, or some interaction between the two. Additionally, many aspects of the climate, such as AMOC, can be hard to diagnose after the 30 to 50 year time scale that these experiments I've talked about are conducted for. And then there's also the question of which hemisphere should you inject more in and why if you want to balance the surface climate. These are 2 other experiments simulated in CESM1 and CESM2. They're similar experiments that Simone conducted using 2 generations of the same model. And in CESM1, you need to inject more in the northern hemisphere, and in CESM2, you need to inject more in the southern hemisphere. And the reason why this happens in CESM and whether it would be similar in other models still remains an ongoing research question. And so the goal of the experiment that I'm about to present is we want to identify the long-term response to SAI with a minimal drift in the background state. And so for inspiration, we look to an old geoengineering model intercomparison project experiment called G2. Which was proposed in the original GeoMIT paper about 15 years ago by Ben Kravitz. And this experiment, instead of using a global warming background, uses pre-industrial control, and then with slow but steady 1% CO2 forcing. And then the original GO2 experiment called for solar dimming as a proxy for stratospheric aerosol injection or some other mode of climate intervention in order to offset the radiative forcing from that CO2 increase. And the experiment lasted for 50 years. So we're going to revisit this experiment, but instead of using solar dimming, we're going to simulate the stratospheric aerosol injection directly. And instead of running the model for 50 years, we're going to run the model for 150 years to try and get a better understanding of how subsurface impacts like AMOC respond over longer periods of time. So when designing this experiment, we mirrored the G6 and the ARISE SAI 1.5 protocols. So we ran one ensemble member of G2 SAI using the G6 injection strategy, where we are deploying equal injection in both hemispheres, and we're only trying to manage global mean temperature. And then another one using the ARISE SAI 1.5 protocol, where we're injecting at 4 different latitudes, and we're trying to manage the 3 temperature-based degrees of freedom. And you can see, similar to the SSP 245 background, our first ensemble member of the ARISE-like scenario with the pre-industrial control background calls for most of the injection to be placed at 15 degrees south. However, as we were starting to run these simulations, an observation that we made is that in the initial years, the ARISE protocol with G2, this is a map of global mean temperature average over the first 30 years, with the black line at 0 being the pre-industrial control average, the red line representing the warming from 1% CO2, and the blue line being the new G2 simulation. Over the first 30 years of injection, we were massively overcooling the southern hemisphere. Basically, the goal in designing this experiment is we want the blue line and the black line to match as closely as possible. And we clearly weren't doing that. We have overcooling in the southern hemisphere. And so in the process of trying to discover why, we revisited our sensitivity estimates for how much does stratospheric aerosol injection cool the climate per unit injection at each different injection site. And so we ran new sensitivity experiments. The original G2 SAI injection rates were chosen based off estimates that we had taken from previous simulations. We did not run new sensitivity experiments because computer time is expensive. And we knew that our sensitivity estimates would not be perfect, but we didn't expect them to be this wrong. We reran the sensitivity estimates, and it looks like SAI in a 1% CO2 background could be as much as 50 to 100% more potent than in the SSP-245 background, especially at 30 degrees south. And you'll recall that for the ARISE protocol, most of the injection is going in the southern hemisphere with significant amounts of that at 30 degrees south. So we ran one more ensemble member of the G2 ARISE protocol, but we gave the feedback controller more freedom to choose injection rates, and we reduced the amount that we were prescribing them based on our estimates of where we would need to put them. And the results were striking in that the controller chose to put most of the injection at 30 north and 30 south rather than at 15 degrees south, especially in the second half of the experiment. And this can have significant impacts on the surface and subsurface climates. So keep in mind that the simulations in the middle and on the right are controlling for the same surface temperature distributions and achieved the same surface temperature distributions, at least in terms of T0, T1, and T2. However, we know pretty well that injections at different points on the planet in terms of latitude can affect AMOC substantially differently. So under the pre-industrial control simulation, AMOC strength is pretty stable throughout. In the 1% CO2 simulation, AMOC starts to decline over the 150-year simulation period. And in our first attempt at the ARISE protocol with G2 SAI, where most of the injection is going into the southern hemisphere, we are reducing the speed at which AMOC declines, but we're not preventing it from slowing down. But then with our 1 degree of freedom strategy, where half the injection is going at 30 north, we prevent AMOC from declining altogether. And then in our last simulation, with the same 3 degree of freedom strategy, but where the controller chose to put more at 30 degrees north, we have the same response as the 1 degree of freedom strategy, where AMOC is not slowing or collapsing at all. And so the significance of this is that we have 2 150-year simulations with the same temperature targets, and those temperature targets being met, but they're being met with different injection strategies by injecting at different locations, and these have pretty significant impacts on the subsurface climate. And so, in summary, there were a number of takeaways that we got from this experiment. Firstly, sensitivity can vary substantially with the background scenario, even in the same model. And this means that when designing SAI simulations in the future, I would recommend we prioritize system ID injections to a higher degree rather than just relying on old sensitivity estimates. Because these small sensitivity differences can matter a lot in the long term. Secondly, temperature targets, the same temperature targets can be met with different combinations of injections. Up until now, bless you, SAI controller and strategy design largely operated under the assumption that injection rates and combinations of injection rates were linear enough that there was effectively only one solution for a given set of injection latitudes in order to meet certain temperature targets. And we see from our results here that over a 150-year period, there is significant enough nonlinearity in the system that this is not the case, and that there are multiple different combinations of injection rates which can meet the same temperature targets. And these different injection strategies can have very different impacts on some of the aspects of the Earth system with that operate under longer timescales, such as the AMOC. And this has big implications, in my opinion, for how we present results, not only to policymakers, but also to other scientists, because even scientists in the field are really fond of making statements like stratospheric aerosol injection does this or marine cloud brightening does that. And we already know that those statements are very rarely completely true because injections at different locations and in different parts of the year can have different impacts on the climate. However, I think this reinforces that point even further that even simulations like ARISE SAI 1.5, we're currently exploring whether it would be possible to meet those same temperature targets on the shorter time scale using different combinations of injection rates, and it's looking like we can. And it's possible that ARISE SAI 1.5 would have looked very different if we had designed our controller differently. So that's all the time I have. Thank you very much. Happy to take questions.
Hi, Walker. Thanks for a great presentation. What's the role of internal variability here in confounding attempts to kind of modulate these? And also, like the AMOC, we can see it in the model and calculate it, but calculating it in the real world and actually knowing how much it's changing in the real world, it seems like it would really kind of confound a lot of these questions if this were, happening.
Shorter simulations in a global warming background. The ARISE SAI 1.5 experiment had 10 ensemble members, and the injection rate distribution, the total amount of sulfate that you need to put in to meet your temperature targets, and the distribution of that sulfate across your injection latitudes are pretty similar across all 10 ensemble members. And so for relatively short experiments, I mean, many of the experiments that we've heard talked about over the last couple of days run for hundreds of years. 35 years is really short in terms of climate timescales. So up until now, natural variability has, in my opinion, played a relatively smaller role in determining how your injection strategy is going to affect the climate. But for longer simulations, it's very plausible that some kind of climate intervention would have to last longer than 35 or 50 years. And it's looking like we will need to pay more attention to that moving forward. Your question about how about measuring AMOC in the real world, that seems like a very good point. I don't know how AMOC is measured or how easily it is to quantify it, but it's not something that we directly control for in climate models with climate intervention, because even in the model where you have perfect information, the response of the ocean, especially the deep ocean, is too slow to adapt your injection strategy to it. It's more about injecting in different places and observing the response rather than trying to actively control for it. So I'm not sure to what extent that would affect our how decisions would be made in the real world. But it's worth thinking about.
Thank you.
I yield the floor. Yeah, no, I yield the floor.
Thank you.
In the interest of time. So next talk is given by Jared Farley, and it's on a climate intervention dynamical emulator. So this one will advance it.
This one, and that one.
Yeah, exactly.
All right, hi everyone. Today I'll be talking about a dynamical emulator I designed for the analysis of climate intervention scenarios and exploring that scenario space. As a very quick bit of housekeeping, defining an emulator for this presentation. For this talk, an emulator is some form of simplified model that captures some behavior of a more complex system. It can be AI and machine learning or not. This one isn't. So for this talk, CIDR, that's the emulator's name, will seek to mimic CESM2 WACM 6's time-varying responses in temperature and precipitation and evaporation, but it's not in this presentation, to SAI forcing. The motivation for using this emulator and building this emulator was initially to look at uncoordinated deployments of stratospheric aerosol injection. Before we do that, we should talk about what I mean by a coordinated deployment. So a coordinated deployment of stratospheric aerosol injection generally involves one actor. This could be a nation or a coalition of nations, and they're deploying some form of global SAI. There is one climate goal, or one set of climate goals that can be all completed simultaneously. And there's one strategy to achieve those climate goals. You're not changing partway through. An example of a coordinated deployment of SAI would be ARISE. You are maintaining your surface temperature, your north-south temperature gradient, and your equator dipole temperature gradients. And you are using a mixture of 30 north, 30 south, 15 north, and 15 south. In general, most SAI simulations tend to fall into the area of a coordinated deployment if they're not system ID. Uncoordinated deployments get a little bit more complicated. So here is one example of an uncoordinated deployment. Philanthropists, backed by their home country, retrofit a fleet of existing aircraft to deploy Arctic SAI to bring sea ice to its 2020 levels. They begin in 2035. So that is sea ice to 2020, deploy in Arctic to 2035. Meanwhile, a nation burdened by heat stress builds a fleet of new aircraft, that'll take about 5 years, to deploy SAI at the equator and restore the global mean temperature back to an even earlier date. So 2000, let's say. That's global mean temperature to 2000, deploy at equator starting in 2040. Meanwhile, a third country notices this imbalance of cooling. There's a lot happening in the northern hemisphere and at the equator, and scrambles to deploy in the southern hemisphere to balance out the ITCZ and bring it back to a level even before we started geoengineering. Let's bring it back to 2035. There. So you can see that this already starts to get pretty complicated. Because I'm mean, oh, go back. Yeah, nefarious actors seek to sabotage deployment and create a termination shock, so we'll chuck those onto the second actor. So the number of factors we have here, we have the number of actors, 3.5-ish. We have the target variable, they're all targeting, where they are bringing that target, what strategy they're using, what injection sites they're using to achieve that target, when they're beginning, any events that happen, a volcanic eruption might also fall into here, and when those events are. And each choice made here affects all the others. You can imagine if we decide to bring sea ice to 2000 levels, all of the decisions here might look different. The main difficulties we have in tackling these uncoordinated scenarios is that there are a lot of possible combinations, probably uncountable. And these uncountable possibilities create widely varying responses. And to run them all in Earth system models would be prohibitively expensive. So how do you explore the scenario space? One method is to use a simpler model or an emulator. Now that we've motivated it, let's start on how we do it. We'll take an SO2 injection and put it into some sort of module that models how the aerosols behave. We use a first order linear-ish ODE, and that outputs the global mean AOD for this injection location. We then take that AOD, plug it into some form of climate variable module, like temperature or precipitation, that tells you what the globe's response is to the injection. We use a semi-infinite diffusion here. You could use a 2-box. And then you take that cooling, you scale some pattern associated with the injection location, and that gives you a scaled pattern. And what you do, if you want to be able to model what happens at a variety of injection locations, is that you have a bunch of these running in parallel, and that you add all of them together. You add them all together at the end. And we are running this dynamically, so you're using Green's functions convolving the impulse responses. and getting the overall temperature response or overall precipitation response at the end. So let's use this emulator and go back to our example scenario where there's a bunch of stuff going on. Up in the top left will be the injections of all the different actors. Up in the top right will be the global mean temperature. Here on the bottom left is a reference for SSP 245. And over here will be the years ticking by in this uncoordinated scenario. So we see our first polar actor beginning to build injection. We see our second one beginning to build as well. We see our first actor actually having to bring down their injection to avoid overcooling. Eventually, they're going to phase out entirely. And here's a termination. Actor 1 restarts injection with what planes they have left. We allowed them half. And as we go to the end of the simulation, we allow Actor 1 and Actor 3 to begin talking and begin a symmetric injection like the G6 SAI 1.5. Some things to note. You can see the bit of a termination shock we had here. It wasn't full, and because termination shocks take 10 to 15 years, the recouping of injection was able to avoid the temperature going all the way back to the baseline. And then we ran this example scenario in a 3-member ensemble in CESM2. And here's how it did. Here we see the global mean AOD. The red line is CIDR. The blue line is the ensemble mean. And light blue lines are all the ensemble members. It does a pretty good job. Does a pretty good job with the global mean temperature as well. You can see that Actor 2 gets terminated before they even reach their injection target. You can see Actor 1's overcooling and them having to phase out their injection because of the actions of another actor elsewhere in the world that isn't even paying them mind. You can see why Actor 3 scrambled to bring that, to bring T1 back to some level that it felt comfortable with. There is a northern bias here that we don't do a good job, or we do an okay job of capturing. This is due to the data set we trained on, which were the 12 teragram step response injections held for 35 years. These create certain patterns, and because AMOC is not captured in these dynamics, how AMOC behaved in that training data is different than how it behaves in this not consistent, gradual injection of stratospheric aerosol injection. Oh, and then over here is how CIDR models the global mean precipitation. Again, it does a pretty good job. I have more to comment here if people want to ask questions about it, especially about the targets and how they give up on their targets. So, going back to why an emulator. Initially, it was because we wanted to tackle scenarios like this. Uncoordinated deployments of SAI where I could change any part of that, and we want to see how the world responds with respect to the actions of others. However, there's more that we can explore here, especially with the wide range of SAI scenarios. One would be the integration with economic models or geopolitical models or some method of determining what the actors in a world with climate change might do. Additionally, because it runs so quick, it's in about half a second on a MacBook Air, you can integrate it live with climate games or with workshops like myself and Babatunde did at the Degrees Global Forum. Additionally, you can use this to extend accessibility and scenario development to those without supercomputer access. Get them at least a sketch of how their scenarios might respond in the climate. And to that end, even more broadly, you can explore it right now. Ish. The site fails on Eduroam. It's integrated into a website. What you do is you go to the reflective website, you go to the simulator, and you go up to this gear and turn on custom injection or variable injection. And that'll gain you access to an entire array where you can put in whatever injection amount you want. Yes, people have put in hundreds of teragrams. It breaks. But this will give you and you can zoom in on any country here, and you'll be able to check how their mean temperature evolves over time and how their water availability, that is precipitation minus evapotranspiration, evolves over time as well. Thanks.
Yeah, I think it's really impressive that the model reproduces the thing. And I mean, that's nice. I know that you only have done it in CESM so far, right?
No.
Oh.
I have done this additionally in this paper.
Because I haven't read the paper yet, I guess.
Yes, you might see by the fact that we have these folks.
Oh, so I've done it. Yeah.
It is also in UKSM.
So then the question is, how different are they? Because we already know that the models do behave very differently. Mm-hmm. And so is there a completely different outcome?
It has a really, that's a great question. It has a tough time with UKSM's tropical pipe. The nonlinearities I put into the aerosol module just can't quite capture how much, when you ramp up injection, just sort of plateaus. And it's had really kind of a tough time dealing with that, but the temperature seems to be pretty similar other than obviously the magnitude of things.
So last talk is given by Sim-Chan Yuk, and it's on the nuclear war in a world brimming with plastic. Here is the...
How can I use the pointer? So the pointer is this one? And you can, this one. So the slide, yeah. Thank you. Thanks for staying until this last talk. Today, I'm going to be talking about imaginary nuclear war and its potential impact on ozone layer, focusing on the role of halogen and organic emissions. So there are two sort of established theories for this line of nuclear war study. First one is the global nuclear war between US and Russia, which is known for its potential for the nuclear winter. And there's another much smaller scale war, like a regional scale war. For example, the war between India and Pakistan, and today I'm going to be focused on this smaller scale war. So previous studies for this India-Pakistan conflict have estimated that, predicted that if India and Pakistan started using the nuclear weapon against their opponent cities, and it will ignite large-scale urban fires, and it will burn everything in the cities. So it will inject about 5 teragrams of soot into the atmosphere, and some amount of organic carbons. And one of the major impacts highlighted by previous studies is that this 5 teragram injection of soot will cause global ozone depletion. Just as a reminder, none of the life on Earth system could have not survived without ozone layer, which protects us from the harmful UVB radiation. So plot on the right shows the result from previous chemistry climate simulation run on CESM WACM. Each line has slightly different assumptions for chemistry and aerosol module, different WACM version, but we can see that the difference across the model is quite subtle, and all models in general predict about 20 to 25% of global ozone loss in first couple of years, and it takes more than a decade to slowly recover to original state. And previous studies
mentioned that these are largely due to temperature effect, since black carbon will absorb short-wave radiation, it will hit the atmosphere, and the gas phase ozone loss reaction will be faster in the warmer climate. So what we are trying to add to this previous finding is to account for halogen emission, because we know that the urban structures and industrial products will have more halogen content. For example, any PVC or vinyl, so cables and pipes and plastic parts of home and cars will include chlorine component. And for bromine, its main usage is in the flame retardant. So any furniture, carpet, or home will include bromine content. So I think it's reasonable to expect there will be a considerable amount of halogen emission if the fire is on the urban areas, not in the wild forest. And one important thing is that both the chlorine and bromine are very effective ozone depleting substances once they get into the stratosphere. So I briefly talk about our some updates in our understanding for the role of heterogeneous chemistry in organic carbon and its role on stratospheric ozone loss. So this plot shows the solubility of HCl for different types of aerosols. So the heterogeneous reaction is faster when the more amount of HCl can be dissolved in the aerosol surface, and it differs by the types of aerosol. So here the cyan color shows the HCl value for the sulfate aerosol, which is typical background aerosol or volcanic aerosols. So it shows quite large solubility values around the 190 Kelvin, which is pretty cold temperature, but it rapidly drops as the temperature gets warmer. So for sulfate heterogeneous reaction, the most important assumption is it needs to be very cold environment. So this only occurs in the polar region during winter time. However, recent studies on Australian fires have found that this HCl solubility in organic carbons can retain much higher values. Here, the red line is the HCl for organic aerosol, and it can retain much higher values for much wider and warmer temperature range, or including this typical range of stratospheric temperatures. And the previous study found that if we account for this heterogeneous chemistry in organic aerosols, then vacuum could reproduce the large ozone loss after the Australian fires. So we used vacuum 4, which is kind of an older version, but it still includes all these important stratospheric ozone chemistry, oxygen reaction, and heterogeneous reactions on sulfate aerosol, and we have updated this for heterogeneous reaction in organic carbon as well. And then we used Chuck Bardeen's karma for simulating the nuclear emission. So we put 5 teragram black carbon following previous studies, and we also add 1.6 teragram of organic carbon and half teragram of NOx and 3 teragram chlorine and 0.08 teragram of bromine as a nuclear emission from urban fires. And those estimations are based on literature survey for incineration study and previous laboratory measurement. So here I'm briefly showing how the simulated plume evolved over time. So the smoke is initially injected in the upper troposphere. It's not working. Yeah, upper troposphere, but it rapidly self-lofted into the stratosphere and spread over tropics and northern hemisphere within first couple of months, and then stayed above 50 hectopascal for the rest of the simulations. So here are some global climate responses to this 5 teragram nuclear emission case. We can see in most of the simulation, there was on average about 15 Kelvin of global stratospheric warming, mainly due to the black carbon's radiative effect. And then this effect slowly decay as the black carbon is being removed from the atmosphere over time. And there are some decrease in this warming in the case with the larger ozone loss because of the ozone's radiative feedback. And if you look at the lower panel, which shows the global ozone burden. Here, the black dashed line is control, and this purple, blue-ish color shows the simulation setup very similar to previous studies by Chuck Bardeen. So we can see at the end of first year, this simulation shows about 20% of global ozone loss consistent with estimate from previous finding. However, if we add bromine, that it increased to 25, and then if we add chlorine, it increased over 30%. And then if we put both of them, these are not linearly additive, but since it's saturated, but we can see about 40% of global ozone loss at the end of first year, just doubling the previous estimate. If you look at the latitudinal pattern of the ozone depletion from this case, plot on your left shows the difference between ore emission case and control simulation. We can see a large mid-latitude ozone depletion over the close by the injected area during summer, and then there's also polar ozone depletion during the boreal winter. And the plot on the right is just shown as reference. This simulation is very similar to what is done in Bardeen et al. And here, most of the ozone loss is occurring in the polar region, and in general, the ozone depletion is much weaker, and we don't see large mid-latitude ozone depletion. So to understand this, the left panel is showing the global ozone. We can see a decrease in ozone across all stratospheric levels. And the plot on the right shows the odd oxygen rate as a precursor for the ozone loss. And we can see most of the total odd oxygen rate is actually coming from these halogen cycles, which include both chlorine and bromine cycles, and some from Hox cycle. And there are some repartitioning for NOx cycle. But yeah, we can see those ozone loss are mainly coming from halogen. So at warmer climate, gas phase ozone loss is faster, but for heterogeneous chemistry on surface aerosol, it's less effective. However, if we include organic carbon, then the situation changes. So here we are looking at the 4 important heterogeneous reactions for halogen activation, and we are seeing large increase in all of these heterogeneous reactions, confirming that with organic carbon, these heterogeneous reaction on the halogen cycles are contributing to substantial global ozone loss. Finally, we are looking at some implication at the surface. So here the upper plot shows the UVB radiation at the surface, and then we can see substantial increase in surface UVB level overlapping with the regions with substantial decrease in column ozone. And for natural ozone depletion, most of ozone loss is occurring over the polar region, but here we can see there are mid-latitude ozone loss, including over the area with highly populated area. So this ozone loss from nuclear war could happening over the mid-latitude cities, posing more health risk for humanity. So yeah, our results show that regional war scenario with a 5 teragram injection case could result in about 40% of global ozone loss. And this is driven by both temperature effect from black carbon and also by the catalytic cycles of halogens. Yeah, so I hope that our result provide one more incentive to not use any of nuclear weapons for any scales. So even for the regional war, the environmental impact will be global. With that, happy to take any questions.
Are there any questions?
So did you only run this for 1 year, 300 days?
I ran for 3 years.
3 years, okay.
Yeah, and for the halogen emission case, since the ozone loss saturation is pretty fast, so the global minimum occurred within first year.
Okay.
Yeah, but I ran it for 2 more years.
And I don't know, maybe I missed that, but did you show that or?
No, I might have.
I was wondering if the these things last a long time. It can be up to 10 years before you get back to normal conditions.
Yeah, for 3 years, it is still, the ozone depletion is not yet to recover. And
I was just wondering with the new chemistry in there that the recovery time lengthens because it's warm.
Yeah, since I think there are more ozone layers, maybe it takes longer, but I haven't looked over 3 years. But yeah, I think that's worth to look at.
I have a question about this type of figures, the one you showed first, but it's the same here. So green is bromine, yellow is chlorine, and red is both.
Yes.
I'm surprised they don't, they add up so less. It's like bromine plus chlorine, when they are both together, they enhance each other. But it looks like the red is quite close to the yellow one.
Yeah, I think it's not linearly additive because the ozone depletion is occurring locally and then it's saturated pretty quickly. But if I test it for smaller, I did run some sensitivity case for smaller emission, then it adds up. Yeah.
The coupling between both, it's larger than each individually.
Coupling between both?
Between bromine and chlorine, I mean.
So you mean the interaction between bromine and chlorine cycle?
Yeah, so it's usually when you add bromine, if you have a chlorine bracket around, the effect is larger than if you don't have it. So it's just the sum of both which enhances the most, like the cross cycles, which I think even in standard lower stratospheric chemistry.
Yeah, I didn't know about that, but okay. Yeah, I will try to see.
That's really interesting stuff. Thank you.
Yeah, thank you.